Hello, I'm Sally Kornbluth, president of MIT, and I'm thrilled to welcome you to this MIT community podcast, Curiosity Unbounded. Since coming to MIT, I've been particularly inspired by talking with members of our faculty who recently earned tenure. Today, my guest is Brent Minshew, an associate professor in MIT's Department of Earth, Atmospheric, and Planetary Sciences. Brent studies how glaciers and ice sheets are changing in response to global warming and other environmental factors, how they affect those forces in return, and whether there are practical ways to stabilize them. His central focus is understanding the processes likely to drive global sea level rise. So Brent, welcome to the podcast.
Yeah, thanks for having me.
Climate change is obviously a growing global challenge, with rising sea levels from glacial melt posing a major concern. As an expert in this field, can you explain the urgency of sea level rise and its immediate and long-term threats?
Sure. So current projections of sea level rise put sea level to somewhere between 50 centimeters to about a meter or so above present by the end of this century. And those numbers alone don't necessarily sound scary until you sort of extrapolate that into the aerial impact of all of this. Right? So what we're talking about, if you take sea levels and you consider the fact that, coastal areas have relatively small slopes, and as you increase sea levels more and more, you start to inundate larger and larger areas over time. We're talking about, even for modest levels of sea level rise, the displacement of many millions of people. And if you go to the extreme end, which is 2 meters of sea level rise, which we think is entirely possible, then you're looking at a displacement of minimum 500 million people, somewhere around in there. That is under current population locations, densities, and so forth. So this doesn't take into account increases in population, the tendency for people to move. It doesn't take into account how the displaced people will end up displacing other people who are inland. It doesn't account for any of that. So at a bare minimum, we're talking about 500 million people or so displaced.
And none of these things are happening in isolation.
That's right.
In the context of, global warming. We've just seen with the LA fires, you're going to have sea level rise, you're going to have
That's right.
fires, you're going to have, tornadoes, you're going to have hurricanes, etc.
And major stress is placed on freshwater resources. Which is something else that we're very concerned about for sea level rise. So the seawater contamination of coastal aquifers. The salting of agricultural fields and so forth. There are all kinds of major implications that come into this. And so, we work a lot on trying to get an idea of what are the probabilities of these different outcomes. As a field, we don't yet have good quantification of the uncertainties in all of this. We can't really tell the world the likelihood of 20 centimeters of sea level rise versus 50 centimeters sea level rise versus a meter versus 2 meters. We're just not at that level yet.
And the average person can't conceive of, as you said, of what that means. It doesn't sound impressive, but it is.
That's right.
That's
right. When I say a meter sea level rise, people are usually like, I've been to the beach, waves are taller than a meter.
Right.
Like, well,
that's
what's,
right.
What's
when you tell
deal?
People 2 degrees,
exactly
increase.
That's
anyway,
right.
So are there particular places that you focus on? What glaciers, pose the greatest threats?
Currently, the Greenland ice sheet is the largest contributor to sea level rise, and that is due to both melting at the surface as well as the acceleration of glaciers themselves. And it's the acceleration of glacier flow, the dynamics of glaciers, that will be the thing that really sets sea level going forward.
So can you distinct for the audience, and actually for me too, the distinction between a glacier and an ice sheet?
Oh, sure. So a glacier is it's a river of ice.
Okay.
So a glacier we would distinguish as areas of ice that are flowing at some measurable speed.
Got it.
Whereas the ice sheet, when we talk about the ice sheets contain glaciers. So glaciers are special parts of the ice sheet where the ice sheet is flowing fast into the ocean.
Got it.
So all ice sheets contain glaciers, but not all glaciers are necessarily parts of ice sheets, because we have glaciers in mountainous regions and so forth. And so, the Greenland ice sheet is currently the largest contributor to sea level. And will be for at least the next few decades, most likely. But Antarctica is by far the largest source of uncertainty in sea level.
I see.
And that is attributable basically to one area, so the West Antarctic ice sheet. And so the special part of the West Antarctic ice sheet is this glacier known as Thwaites Glacier. And so Thwaites is a very special place. It's the only place like it in the world, really. And West Antarctica is unique in the world in that it is what we refer to as a marine ice sheet.
Mhm.
And what a marine ice sheet means is that it is an ice sheet that is resting on the seafloor.
I see.
So the bed of West Antarctica is about 2 kilometers or so
Mhm.
below sea level,
Wow.
roughly on
Yes.
average, somewhere around in there.
Mhm.
And the ice is in contact with the bed just because it's thick enough
I see.
to be in contact with it. So as the climate warms, as we start to lose mass from West Antarctica, it thins.
Mhm.
It has to, and that peels off big areas
I see.
of contact between the ice and the bed. And that's incredibly important because, especially in Antarctica, more or less 100% of the mass loss, the ice mass loss from Antarctica, its contribution to sea level rise, is due to the flow of glaciers because
Mhm.
Antarctica is very cold.
Yes.
You get relatively little surface melt.
Yes.
And the flow of glaciers is very sensitive to how much drag there is at the bed, at the
Mhm.
base of the ice. The contact between the ice and the dirt or the rock that's underneath it.
Mhm.
Right? And so most of its resistance is going to come from the contact between the ice and the bed. So as you thin this, because it's submerged,
Mhm.
as you thin, you peel large areas of the ice off of the bed.
Okay.
So it's like taking your foot off the brake in your car.
I see. So the
And so
flow
all the ice
increases of all
starts
the.
flowing
I see.
faster.
I
Right?
see.
And because mass is conserved, once you flow faster,
Yes.
then you also have to thin faster.
I see.
And so
Yes.
there's a runaway effect
Yes.
that we refer to as the marine ice sheet instability, which is a buoyancy-driven instability.
I see.
That
I see.
that a lot of research suggests that we're either very close to or already in this state of instability. This is now that basically mass loss from West Antarctica could at this point very well be driven by internal feedbacks
Yes.
and thus
Yes.
insensitive, or at least largely
Yes.
insensitive to some extent to whatever we do with emission.
Is there anything you think, even if we were to stop all emissions, tomorrow?
Yeah.
Is there anything that can be done to stop this, escalating effect?
The answer to that question boils down to whether or not we're really in this unstable
Yes.
state.
Yes.
Again, a lot of research over the past decade or so provides evidence to suggest that we are already in this unstable configuration. And if that's true, then we could pull CO2 concentrations back to pre-industrial levels
Yes.
tomorrow, and
Yes.
it wouldn't stop
Yeah.
the
Exactly.
demise of West Antarctica.
So it's more adaptation at this point than.
It could be. I mean, those are currently the only options on the table. I should also mention that if Thwaites goes, the idea of projections that we mentioned before, the potential for 2 meters of sea level rise by the end of the century, that's primarily due to what happens to Thwaites.
I see.
That's the big uncertainty.
I see.
And so currently adaptation is the only set of options on the table for us. My group here at MIT, as well as a few other colleagues across glaciological community, are starting to address the question of what else can we do about this.
Yes.
And so we're working on this question of basically, can you engineer Antarctica
Yes.
to try to stabilize
Yes.
the ice sheet? And we're in the very early stages of doing this, and we have there are some rough ideas on the table.
Yeah. What kind of things can you do to?
So there are basically three
Stabilize.
broad categories of ideas that have been presented. So one of the earlier ideas that was presented was basically pumping a bunch of seawater onto the ice sheet and blowing it out as snow.
I
And
see.
so you just increase the mass over
Yes.
the ice sheet. And there have been a few papers published on this, and it's not clear to me that could work, that you could scale that.
I
The
see.
ice sheet is big.
Yes.
Thwaites Glacier itself is the size of Florida,
Wow.
right?
Wow.
And so
There's a lot of snow.
Yeah. West Antarctica is a considerable fraction of the continental United States.
Yes.
These are huge,
Yes.
huge areas that you would have to deal with
Yes.
and distribute snow across, and you'd have to pump water in many cases over maybe a couple hundred kilometers
Yes.
of ice in air temperatures that are usually not much warmer than like -10°C.
Right.
Right? So you'd have to do all this without the water
Right.
freezing.
Yeah.
There's all kinds of challenges with that. Another sort of category of ideas has to do with the fact that in Antarctica and Greenland, in Antarctica especially, the mass loss is really driven by the warming of the seawater local to the ice sheet. So the transport of warm, deep water
Yes.
to the ice sheet itself, that's melting the underside of the ice, and that's particularly challenging. Ice is a truly amazing material. So if anybody's listening out there
Yeah.
is excited about material properties, you should totally study ice.
Okay.
It's not very well understood, and it's a fantastic problem because of its elegance. It's just two hydrogens and an oxygen.
Yes.
but it has all of these fantastic material properties.
Mhm.
It floats, for one thing, which is one of the
Yes.
reasons why we're concerned about what's happening in West Antarctica. And because it floats, expands when it freezes, that means that when you put it under pressure,
Yes.
you depress the melting temperature.
Okay.
Right? Essentially what happens is that you have warm water that's coming in and it's touching the glacier at exactly its most vulnerable point,
Yes.
which is the deepest part of the glacier, where it's the easiest to melt.
Okay.
Right? And so, melting temperatures in Antarctica will be, a degree or so
Oh, wow. Okay.
off from the standard 0
Yes.
degrees C. So it's much easier to kind of to satisfy the sensible heat budget, basically,
Yes.
and melt the ice in these cases.
And that sounds like it can be a positive feedback loop.
Exactly.
Yeah.
Yeah, there's actually a local pumping effect where the warm water comes in and it melts the ice. And the ice is just compacted snow, so it's
Yes.
fresh. So whenever it melts, it's fresh water, which is buoyant in the salt water
I
in
see.
the area. So it has to rise, and it creates these
Yes.
turbulent plumes that go up. And that creates this kind of like almost self-sustaining pump where the ice sheet pulls more
Yes.
and
Yes.
more warm water toward it. And so, this class of ideas that we were talking about for, engineering Antarctica,
Yes.
thinking about how to intervene to slow rates of sea level
Yes.
rise. And one of them is, well, what if we just block that warm water?
Okay.
If it's warm, deep water that's coming in
Yes.
and it's coming into contact and melting these
Yes.
glaciers, why not put a
Right.
barrier
I
on
see.
the ocean floor to try to block that warm water? And this is
That's
probably
interesting.
one of the better developed
Hmm.
ideas. It's still very much in its nascent stages,
Mhm.
relative to the complexity of the problem.
Interesting.
Um,
I mean, this sounds like an engineering challenge.
Yeah, I mean, it's a huge challenge. This one also, you run immediately into questions of scale.
Yeah, exactly.
How would you
How
put
big a wall do you need?
exactly like
Yeah.
how would you put almost certainly tens of kilometers
Yes.
long at its minimum,
Yes.
and how do you put that in the most remote area on Earth
Exactly.
that is often inaccessible to ships due to sea ice cover and
Yes.
so forth? And then last category, this is stuff that I'm most interested in. Because it has the potential to actually stabilize the ice sheet.
Mhm.
So all these ideas of instability that we were talking about before, they're predicated on the assumption that the ice is thawed at the bed and it is sliding over its bed.
Okay.
And so if you could freeze the glacier to its bed,
Okay.
then that is a stable configuration.
I see.
And most of the edges of the ice sheet are frozen to their beds, and
Okay.
they're relatively stable. We're not too concerned with them. And glaciers in Antarctica do freeze themselves to the bed.
Right. So you're going to stop the
part of the
glacier
natural-
flow.
Yeah, that's
Yeah.
right. And they do this to themselves as part of the natural process. And so we have natural analogs, natural phenomena that we can work on and we can learn from.
Mhm.
And our current understanding of why glaciers in Antarctica freeze themselves to the bed sometime is that there's a thermodynamic feedback. And basically what it is that glaciers in Antarctica are flowing essentially because they're flowing, to a good approximation. And what that means is that the flow is facilitated by the lubricating effect
Okay.
of the water that's
Yeah.
produced by the melting of the ice
Yeah, I
itself.
see. I see.
And in areas where the glaciers are flowing, the primary source of heat is the frictional heating
Okay.
that takes place
Yes.
due to the flow. And so you create this actually interesting feedback loop where the drag at the bed, the resistance
Yes.
of the bed, influences the velocity of
Okay.
the glaciers, like how fast they're flowing. And then the product of those two things
Mhm.
gives you the heat source,
Okay.
right? And so this is an interesting problem where to a good approximation, the driving force remains constant,
Hmm.
and both the resistance and the velocity change together.
Right.
And they change together in a nonlinear way. And the nonlinearity just comes from, again, the properties of ice, because ice is an amazing material.
Right.
And it comes from the fact that viscosity has a stress dependence to it.
Hmm.
So the higher the stress, the lower the viscosity. And so when you sort of take all these things into account, what you create is a situation where you can manipulate the drag at the bed,
Hmm.
or the friction at the bed, or
Mhm.
whatever, however people want to think about it. You can change the drag at the bed such that there's no resistance at the bed,
Hmm.
right? So perfectly lubricated,
Okay.
like floating ice. And so you
Okay.
produce no heat. And then on the other side, the drag is so high that there's no velocity, that the glacier
Right.
can't flow anymore. So you also produce no
So
heat.
you could manipulate it in either direction.
Exactly.
Okay.
And so it also means that because there's heating in the middle and it's zero at both edges, then there must be a maximum somewhere.
Yes.
So there has to be a point at which if you increase the drag more,
Yes.
you reduce the rate of heating,
Okay.
which is counterintuitive, right?
Yeah, I understand.
Yeah. But then that creates its own self-sustaining feedback loop
Yes.
where the glacier kind of gets itself into this mode where it starts to freeze itself to the bed.
I see.
And so the idea then boils down to basic ideas boil down to then how do you increase
Exactly.
the drag at the
Right.
bed?
Exactly.
Number one, flow is facilitated by the lubrication of water
Mm-hmm.
at the bed, right? So one obvious solution is then, well, you drill a hole and you pump water out from the bed,
Oh, interesting. Okay.
like draining the oil out, out of your car engine while it's running,
Right.
right? It's eventually going to slow things
Right.
down. The second one is that, well, the water is all supplied by melting at the bed itself.
Yes.
And so if you just actively cool the bed, then you starve everything of the water. And then the third one is you would construct obstacles at the bed, which I don't think that the obvious approaches are going to work where you like build a concrete barrier or something
Right.
like that. But there are ways, things that we understand in the physics of the system where you could manipulate water pressure and other things to get the glacier to sort of drive itself down into the bed.
Yeah,
This
I
is
see.
something that they do naturally.
Yes.
And so you get it to like effectively ground itself. And so the logistics of this, how do you actually do this? I'm very excited about an idea that uses these things called thermosiphons. And a thermosiphon is nothing more than a heat pump,
I see.
but it's a passive heat pump.
Uh-huh.
So it works like the heat pump in your house, or there's a heat pipe in your computer.
Mhm.
We use these things all the time. The nice thing about the thermosiphon is it, at least in our preliminary work modeling these things, it appears as though the difference in temperature between the bed and the surface of the ice
Mhm.
is enough to drive the heat pump
I see.
itself. So we're taking advantage of the energy that
Yes.
is already in
Yes.
the system
Yes.
to drive this. And so the way it would work is you would basically drill a hole from the surface to the bed,
Mm-hmm.
which is something that we do.
Yes.
We have the technology to do this. And you drop in a vertical pipe
Okay.
to, pretty close to the bed. That pipe will be filled with pressurized CO2.
Okay.
CO2 seems to be the best working fluid that we have.
Okay.
And it's pressurized to somewhere around, 400 to 500 psi. And the reason that you do that, of course, is that at those pressures and under the temperature conditions that we see in the ice, the CO2 is going to be a liquid
Yes.
at the base of the pipe.
Okay.
And then it absorbs heat
Okay.
because
And it melts.
again the bed is the the
Well,
bed is
not
the
melts,
warmest
but
part. It evaporates.
Evaporates. That's the word. Yeah.
Yeah, and so and then the vapor rises to the surface
Yes.
where it recondenses,
I see.
releases its latent heat to the atmosphere.
Yes.
And the amount of heat that we're talking about is trivial compared
Yes.
to what the atmosphere
Yes.
can handle. So, when we're talking like milliwatts per square meter
Yeah.
of heating, right? It's very small, but it's enough to manipulate the glacier. And so, once it recondenses at the surface, of course, it just rains back down
Yes.
to the bottom, and then this process
I see.
continues.
I see.
There's more fluid dynamical complexities involved, but that's the basic idea.
So how many
behind it.
years are we from being able to go from modeling to actually, pilots, things like that?
Well, that's the $1 trillion question. I don't know. I think that we're spinning up efforts at sort of ever increasing scales. We're starting small and growing in terms of bringing in funding, attracting more people
Yes.
that have relevant expertise and these kinds of things. Like people who engineer thermosiphons. I should also mention that thermosiphons have been used for many decades to stabilize foundations in the Arctic.
Oh, okay.
This is a very common tool. If you look at pictures like the Transantarctic Pipeline, you'll see all of the legs of the Transantarctic
I
Pipeline
see.
have these fins on
I
top of them.
see.
Those are thermosiphons.
I
There's
see.
120,000
I see.
of them, and they're meant to keep the permafrost frozen
Yes.
so that it provides
Oh,
good
interesting.
stability for the pipeline.
So this is sort of a writ large adaptation of these technologies.
Yeah, that's right.
Yeah.
They've
Very
been around
interesting.
for a long time. I mean, of course, we're looking at longer thermosiphons than currently exist,
Sure.
but all of our initial modeling and our early stage discussions with actual thermosiphon engineers that
Yes.
have been doing this
Yes.
for decades suggest that it should work. And there are some field trials of long thermosiphons that have been done for geothermal applications because the geothermal field is very interested in thermosiphons for moving heat up. It's an extremely efficient way to move heat from one place to another.
Do you, maybe you can say, I think people would be interested in what it's like to work in Antarctica. In other words, what are the adaptations just for, human beings to be there in such an inhospitable environment? When you talk about the surface temperatures, et cetera, it sounds,
Yeah.
I think Boston's cold.
Yeah.
That sounds crazy.
Yeah, it's certainly cold there. So unfortunately, I'm not the right person to ask for this. I got into this line of work so that I could go to Antarctica and do stuff, but for one reason or another, it's never worked out. So I've never actually been to Antarctica.
Amazing, yeah.
So I do, we do theory and we do satellite observations and
Yes.
so forth, and work with a lot of colleagues that have been to the field. And the short answer is it's cold and it's windy, and it's just kind of like that some of the time. And then other times, at least during the summer when people are actually doing field
Yes.
work, during the austral summer, it can get up above freezing.
I see.
In some areas that people work. And so there's, I never cease to be amazed by how many pictures I see of my colleagues in like short sleeves
yeah.
working on things, because they're actually out there doing work and then the sun's shining on them.
Yes,
and all that. And so they're fairly warm. But as a general rule, it's very cold. And Thwaites has horrendous weather.
Huh.
It is definitely one of the most complicated places on
Mhm.
Earth to work. And the weather is just really terrible. So one of my students went down a couple of years ago to work in Thwaites.
Mm-hmm.
And she was in Antarctica for 2.5 months.
Wow.
Waiting to be able to go to the field.
I see.
And then she was in the field, I think, for something like 10 days. But they were snowed into their tents for like 7 of them, somewhere around in there. So they got about 3 days worth of work done for the year.
Wow. Wow.
And so that's like, that's a little bit unusual.
Yes,
It's not always
yes.
that bad, but that is an anecdote that's
illustrative.
illustrates
Yeah.
one of the considerations. So when we're thinking about things like, could we actively stabilize Thwaites? So we have in mind the fact that this is like one of the most inhospitable places on Earth to work, and even under the best of conditions, you're only going to be able to work for 3 to 4 months out of the year.
Yeah, exactly.
Down there,
and it sounds like even in the more hospitable months, you can face unpredictable challenges.
Yeah, but we think that back of the envelope calculations, at least that we've done, if we're thinking about like how many thermosiphons would it take
Yes.
to have an effect in this area. Even the natural analogs teach us that that glaciers can stagnate if only a relatively small area of their bed is frozen.
So you don't have to get it to adhere all the way across.
You do not need to freeze a Florida-size patch of the ice. If you do it in intelligent ways, and you think about it in the right way, and all of this will come out in modeling, then a relatively small patch of ice will have a large impact on the overall flow speed. And so what that basically means is, then if I go in and I freeze a small patch right in the middle of this glacier, and I cut it in half, then I reduce its mass flux, its contribution to sea level by a factor of 16.
Wow.
Right? And that would just be, all I need to do is cut it in half.
So it's like pinning it.
You just pin it in place. And let's just say, as a conservative estimate, we need to, place 10,000 of these thermosiphons within this square area. Then that's arguably doable.
Yeah.
And you have multiple crews, you have multiple drills.
Yes.
You get crews to the stage that they can drill a hole in a day and a half, somewhere around in there. You get a few months of working time. You scale according to these crews and recognize that you don't need to drill 10,000 in a single year.
Yeah.
You could spread this out over a decade and start having effects and so forth. Then it gets to the realm of kind of being realistic.
Right. So let me switch gears a bit in our last part of this. So I read that you joined the Marines at age 17, excuse me.
That's right.
What attracted you to the Marines?
A variety of things. Maybe the most important considerations are that it was something that was seemed like a real personal challenge. Mm-hmm. And at that age, I really wanted to test myself and to understand what I was made of and what I was capable of. Mm-hmm. I joined the Marine Corps in 1995, so when I was at the beginning of my senior year of high school. And of course, at that time, this is obviously pre-September the 11th. And so there were no large-scale wars. And if you watch the news at that time, the Marines were out doing a lot of humanitarian aid in these very difficult situations and so forth. And so I saw this as this opportunity to get out of my small town, see the world, to go to very challenging environments and challenging places where people needed help, and to hopefully actually help them, to do some good in the world, and then to learn more about myself in the process and all these challenges. And so I really wanted, when I was 17, I really wanted to be that person that,
Yes.
that you could send into the most difficult and dangerous places.
Yes.
And like, and I could just get it done. And I had no idea when I was 17 if I was capable of that.
Yes.
Or anything like that. But I really, really wanted to do something like that. And in many ways, I was extraordinarily lucky in my career. I got to have a front row seat to many major historical events of that time and to participate in them. I was with Marine One for a while. I flew Yasser Arafat to Camp David.
Wow.
The last time that there were serious
Yes.
peace talks between the
Yes.
Israelis and the Palestinians. And so I got to be there for that. I was at the Pentagon on September the 11th.
Wow.
And so I got to play a role in,
Yes.
helping to evacuate the Pentagon,
Wow.
which was, a real honor, I think,
Yes.
to be able to play some role. Like, obviously, I wish the event wouldn't have happened, but if it was going to happen, I'm really happy that I was there to help.
Yes.
And
Yes.
there to do something meaningful.
Yes.
I was one of the first Marines on the ground in Iraq. I was with a unit. We were all by ourselves in the north. And in Mosul, we did some counterterror things in the Eastern Horn of Africa, so Djibouti, Somalia, Ethiopia, that area. Got to spend a summer in the Eastern Horn of Africa, which, if you're not used to heat, I
Yes.
strongly advise
Not
not doing.
going.
It is. I'm from Texas, and I thought I knew what heat was, and I was
Wow.
wrong.
Yeah,
I was
yeah.
very, very wrong. And then finally, I rounded out my career. We intervened in the Second Liberian Civil War. And so we went in and we put an end to hostilities and kind of provided this level of security that allowed UN peacekeepers and UNICEF and these other organizations to come
Yes.
in and bring food to the people who were effectively being starved. And so I got to end my career finally doing the thing that I wanted
to do. We like to think about MIT as being a place where people tackle hard problems, but it sounds like you had encountered many difficult problems and challenges before you ever got here. How did you wind up going from a 17-year-old Marine to a geophysicist studying glaciers and sea level rise at MIT?
Accidentally, in some ways, I guess. I like to take the nonlinear approach to life. After I got out of the Marine Corps, I went to college. I didn't know what I was going to study, didn't know what I was excited about. I just knew that I wanted to do something different. And when I was a kid, growing up, my mom worked at the Johnson Space Center, and I remember going there as a kid and always being enamored by flight, and
Sure.
John Glenn was my hero.
Yeah,
and, all these kinds of things. John Glenn was a Marine.
Yes,
know?
yes.
And so hopefully you see all these connections,
Yes.
like spokes on the wheel of my life. But I decided to study aerospace engineering. I wanted to build rockets and do cool stuff like that. And so while I was doing my undergrad, I learned a lot of stuff, and I got very excited about formal education again, which I was a little bit burned out of. So I decided to just continue and get my master's in aerospace engineering. And while I was doing my master's degree, I went to a seminar because they had free food there. I knew nothing about
as graduate students do.
As graduate students do. So I went to the seminar, and it was about interferometric synthetic aperture radar, which is just a particular way of measuring motion. It's the kind of thing that we do now in my group to measure glacier motion and so forth, and how it changes. And I had never heard of anything like this before. I had never really encountered the idea of remote sensing in general.
I see.
Like what more you could do from satellites other than take pictures.
Right.
And I just thought it was the greatest thing since canned beer. I mean, it was just amazing. And I got really, really excited about that. And I changed my entire master's thesis direction to learn more about that. And I managed to work out getting an internship at the Jet Propulsion Laboratory because that's where the people were that were building these radars and had developed all this process. And I was really, really excited about it. And so I wanted to go work with them. They had this experimental airplane and radar. It was just, I was a kid in a candy store. And the first summer that I was out there working on this, I happened to just bump into the person who would become my PhD advisor in the hallways, just randomly. And so we started talking about things, and I told him that I was interested in learning this because I really wanted to study glaciers and learn more about Antarctica, because Antarctica seemed cool. It was like this sense of adventure.
Yes.
He encouraged me to apply to Caltech, and I got in, obviously. And then, and that, I guess as part of all of that process, I came to discover that it was possible for me to make a living as a scientist, which is not something that I had ever considered.
Yes.
It was not something that seemed like it was available to people like me. And that summer was very much life-changing. And the rest is
history.
Yeah, I mean,
Well, that is nonlinear.
Well, the rest is like the standard story.
Right.
You learn a little bit, you do this.
That's right. You
learn
publish
a little bit,
papers.
you do this, and an opportunity opens up here, and you're like, oh, maybe I'll go through there. And I have been very fortunate to be presented with a number of opportunities that I took.
Well, fantastic. This has been a fascinating story. I've learned a lot, and I'm sure our listeners will have learned a lot. So thank you. And to our audience, thanks again for listening to Curiosity Unbounded. I hope you'll join us again. And I'm Sally Kornbluth. Stay curious.